I'm really excited. I'm really excited to talk about Sarah's research today from the Predator Prey Project. And I know we're pretty quick on time, so I'll just jump right in. Sarah had 4 chapters in her dissertation, and I'm going to talk very, very briefly on chapters 1 and 4 and focus most on chapters 2 and 3, which highlight predator-prey interactions both spatially and temporally. So I'll start with her first chapter and just mention that this chapter was published in Ecological Applications earlier this year. And in this particular chapter, Sarah made use of the massive data sets that we have from the Predator Prey Project, both on the collaring side and on the camera trapping side, to ask this question: are we telling the same story, comparing inferences from camera trap and telemetry data? And the reason I wanted to highlight this particular one is because it really is an important piece for management, because we want to think really hard about what is the best way to answer our questions when we're trying to monitor one species, multiple species, and we have to balance lots of different objectives. So in this particular case, Sarah looked at habitat use and the different models and ways that we might get that information from telemetry data versus collar data. So the big picture is we found at a course level, we had really similar results between the 2 methods. But when we sort of honed in onto finer scale, we found there were some inconsistencies. And that's because there's just fundamental differences in how we collect data from animals that are collared versus camera trapped. And just for an example, when you put a collar on an animal, you get a lot of information about that particular animal. And when you put a camera out, you get a lot of information on different animals, but maybe not as much about one species. You also have to think a lot about different study design. So essentially, deciding which method to use is a matter of what's your objective, what level of detail do you need, and then all the other main considerations: cost, time, safety, and then again, like the type of information. So in this particular case, it was really valuable because we could think about the different questions that we can answer using telemetry data versus collar data. And you'll see that I'm going to talk now about some things that we can do with the collar data. So in this chapter, Sarah looked at species interactions in relation to animal movement. So just as a background, we know that obviously animals move, and they move in different ways when they have different behaviors. So we can expect that things like predator-prey encounter rates are going to vary with movement. So in some cases, we might expect faster speeds depending on the way that an animal hunts, or we might expect randomness of movement in the way that a predator responds to a particular prey. So we can see that prey are likely to adjust how they move to minimize their predation risk. And we expect that that's going to differ based on the predator's hunting mode. So a stalking predator, one that might be more of a sit and wait, versus a coursing predator that's going to be out in an open area, moving faster while they're hunting. So those were our kind of underlying expectations. So the question was, does predator hunting mode influence animal movement in a heterogeneous habitat or landscape? So we expected that the prey species would change their movement in response to a predator's hunting mode to reduce encounters with that predator. So I've got an example here of 2 of our predators, one being more of a sit and wait, and we might expect that prey will respond differently in different habitats. So if you're a sit and wait predator, you might be more likely to be in areas that are rugged, that have more camouflaging, versus a coursing predator where you're going to maybe choose areas that are more open. And we expect prey to respond differently then in those different habitats. We also expected that the predators would change their movement based on their hunting mode, the habitat that they're in as well. So how do we answer these questions? We're going to use a hidden Markov model, and I'll just very briefly explain the idea behind the hidden Markov model. For each animal, we get from the telemetry data a location, and that's represented by the green dots here. And between locations, we can look at how far apart they are, the step length, and we can look at the turning angle, how much the animal has moved in a different direction. And we can use those pieces of information to try to infer differences in a behavioral state. So in this case, we might have these longer movements into an exploratory state, and then these smaller ones into an encamp state. And I just want to emphasize that these are two behavioral states, and we can think about how they might relate to behaviors, but these are unobserved. So the model is just placing the difference in the movement pieces into two categories, and then we're inferring from that what those categories would represent. So we don't actually know exactly what an animal is doing when it's in an exploratory state versus an encamped state. So we had data, thankfully, from all of our predator-prey project collaborators, where we had over 300 GPS collared animals. And in this example, or this analysis, sorry, we used 3 ungulate species that were collared in the study areas: elk, mule deer, white-tailed deer. And then we had 4 predatory species, 2 that we considered as stalking predators, cougar and bobcat, and 2 that we considered as cursorial predators, wolves and coyote. And then we used that 2-state hidden Markov model to look at the behavior of the predators and the prey in response to one another, as well as habitat features. I think probably everyone's pretty familiar with the predator-prey project, but I just wanted to give a quick glance at the study areas. So we have what we call the Okanagan study area in green, and the Northeast study area here as well in green. And the collared animals come from those 2 different study areas, but the prey species we have in the Okanagan mule deer, and then in the Northeast we had collared the white-tailed deer and the elk. So in addition to just thinking about predator-prey interactions, which we used a resource selection for, so we used basically a model to tell us where the predator and the prey were most likely to be on the landscape, and we're going to use that as a covariate. And then in addition to that, we looked at structural complexity of the habitat, which is always important for how animals are moving, and we looked at landscape permeability. I'm really only focusing today on this resource selection part. So that's the part that's telling us essentially how likely the predator or the prey are to be in a habitat. So we use that as a covariate to think about how the other species, so if it's a predator, we have the prey species as a covariate. If it's a prey, then we have the predator as the covariate. So there's a lot going on in this figure, and I'll just try to walk through it quickly for you. The large takeaway message is that ungulates actually changed their movement state and moved less in response to predators. So here we have what we call the probability of being in an exploratory state. So the higher that is, the more likely you're in that exploratory state. The lower it is, the less likely you are. So then you become in that encamped or less moving state. We have in that kind of greenish color elk, and the solid line is summer, the dashed line is winter. The orange here are mule deer, and the purple are the white-tailed deer. And then the x-axis is the relative probability of selection. So essentially, as you go from the left to right, you go from less cougars to more cougars. That's sort of the pressure idea. So in this case, you can see all of the species of ungulates, elk, mule deer, and white-tailed deer, had that response, whereas there are more cougars, they became more likely to be encamped. Very flat line here, though, for elk in the summer. And then exactly the same responses for wolves. Some of them maybe not quite as strong, so you can see the slope of the mule deer is a little bit different, whereas elk, we do see a response here. Now we can flip that and look at how the predators are changing their movement in response to the prey. So along the bottom, I have elk, mule deer, and white-tailed deer. And again, on the axis, it goes from less likely to have an elk there to more likely. And then we have 3 colors here: cougar, coyote, and wolf. So the cougar are pink, coyote are the yellow, wolf are blue. So for cougar and wolf, we have an increase in their likelihood of becoming exploratory as there are more elk. For the mule deer, we see a little bit of a mixed response between the predators, and similarly for the white-tailed deer. So in general, we just had pretty much different responses from the predator to the different prey species. So overall, ungulates reduce their movement regardless of the predator hunting mode. So that means they were moving less, which could indicate increased vigilance as they assess kind of immediate risk. And what we can say from that is that we didn't see any difference in their responses to wolves. So that addition of wolves to the landscape did not appear to change their movement at the scale that we're looking at. So again, it's always important to think about that. We had 4-hour fixed rates on those collars. That is a little bit of a coarser temporal resolution. We also saw that predator movement changed based on prey type. And one thing I want to emphasize here is that a lot of the species also changed their movement behavior in response to habitat features. So we can go back into and think about the different habitat features related to the different prey. As you saw there in mule deer and elk and white-tailed deer were in the different study areas. So there could be habitat features that are also motivating that. And it could also just be due to a more generalist predator movement. One other thing to emphasize is we don't really know that these observed changes in movement actually changed the encounter rates, right? The expectation is that a prey species is reducing its movement in some cases to reduce its risk. That's not something we could tell with the data that we have, but higher resolution collars, more collars, that type of information could help to answer that type of question. Now I'm going to move on. That was pretty much spatial avoidance or interactions. Now I'm going to move on to temporal. And I want to go through this quickly. So the question here really is, how do prey species potentially avoid predation risk in this multi-predator system? So we had two essential hypotheses. One is risky places. So in this case, if an area is a high risk, a lot of predators, or that we know they're there, or the terrain is likely to be where they're hunting, we expect that the prey would proactively avoid those areas. So in this case, we expected prey species to shift the time of day they might be active to avoid predators. And then there's a risky times hypothesis. So in this case, we expect this reactive response to maybe an unpredictable or an immediate risk. So what we're thinking here is that in this example above, if you have a cougar show up in a location, we might expect a long delay before we would see a prey species because it's a reaction to them showing up at that space and time. In order to answer this question, we used those camera trap data. We had 120 camera traps across the study area. They were placed on roads and hiking trails and game trails in order to increase our detections. And we had them out for 3 years. So there's about 360 cameras at different sites over the 3-year study. Again, we used the same species and we looked at summer, fall, winter, and spring. And then we also added black bear and moose because the cameras can capture a whole suite of species. So we were able to include those two in our analysis. One thing that we also wanted to define here was what might be a riskier area. So we used terrain ruggedness as a way to classify habitat as risky or not. And so the assumption was that more rugged habitat would mean an increased risk from stalking predators, and a less rugged area would mean an increased risk from those cursorial predators. So again, using that hunting mode to motivate areas of risk. And what we did was compare daily activity patterns. So in this example, this blue line is the daily white-tailed deer activity. The orange is a daily cougar activity. And this is based on the times that we have photographs on the camera traps. And we can compare then their predator-prey overlap. So the gray area is that time, is the amount of time that they're both active at the same time. And then we compared this type of overlap, both in an area without or with lower risk, as we called it, and with higher risk, so based on that terrain ruggedness. And here's what we found. We found some avoidance of the risky places. So in this example, you can see less rugged terrain, which we would expect to be less risky for the cougar hunting. We have about 0.78 overlap, so 78% overlap in the time. And then in the more rugged terrain, which we consider more risky when you have the stalking predator, like the cougar, Now that percent overlap goes down to about 0.53, so about 53%. And you can see deer became more active in the day when the cougars were less active. And we saw that for both deer and moose, that they generally adjusted their activity to avoid what we called risky places. And this was particularly in response to cougars where we saw that. The next thing we looked at was what we call the time between detections. So I described that a little bit already. We have our cougars show up. You can see the dates on the top. And then we have a white-tailed deer show up. And the time between these detections was 10 days. So what we did was we looked at every single time that we captured a cougar and then the next event of a prey. And we did that for all the predator and prey combinations. And then we used generalized linear mixed models to look at the effects of the predator species, the season, and again, that terrain ruggedness on the time between detections. So if there's no response to a predator, we would expect the time between detections to always be the same. And if we think there is a response, then we would see that that time gets longer between a predator showing up and then a prey. We also included other prey just to give ourselves a comparison. And here's what we see. This is for the mule deer. We saw that that latency of time varied. So here we have the number of hours between detections and then each of the species. So in this case, if you look at wolf, this means we have a picture of a wolf followed by a picture of a mule deer. And the time between that on average was about 60 hours. So overall, we had longer times between our apex predators, a little bit shorter time between our mesopredators, and then shorter times between, oh, I'm sorry, my little arrows got moved there. These are, this one should also be over the coyote and the black bear. And then the last one is ungulate to ungulate. So this pattern is what we would expect if there's avoidance. So what we found is that prey did avoid those camera locations after a larger predator presence. And in this particular example, I'm showing you our best scenario, which was for mule deer. So basically, we found species-specific responses to both that risky places where they're showing up in higher risk places and shifting their daily activity, and the risky times, that latency. And it may be that we found like not all ungulates did both avoid risky places or risky times. And we also found a lot of seasonal variation. So essentially, it seems that the responses also varied by the predators. So there's probably some balancing here where they're having to say risky place versus risky times and coming up with a strategy which basically balances having a bunch of different predators and mesopredators in the system. And I'm pretty much over time, so I'm just going to jump to the bottom. Sarah talked about the effects of grazing and hunting on in the January commission meeting, and that's recorded as well. So you're welcome to go watch that. But another thing we did look at was the effects of how grazing and cattle allotment affected co-occurrence of predator and prey, as well as hunting. And the takeaway here is we found differences for deer based on using public land during the hunting season and changes in their co-occurrence. We also found that hunter activity, the number of photos of hunters, impacted bobcat, coyote, wolf, and moose occurrence. It actually had a positive effect on them, but a negative effect in one case on our co-occurrence. And we also found that animals shift their daily activity patterns as well. And here's just one example where you can see a white-tailed deer, the white-tailed deer activity patterns shifted in relation to hunting activity, as well as predators. So what we found was, oh, I'm so sorry. This is, the deer did not change during hunting season. They changed during, they increased their activity during when there were cattle present. They didn't change during hunting season. However, the predators became more nocturnal during hunting season. So let me think, I have like one kind of, here we go. Essentially, one of the big things we saw was that ungulates were using private land during hunting season, and that possibly is to reduce predation risk on private lands. So it's possible that the private lands may have that potential to mediate some of the possible predator-prey interactions. An important note that we didn't consider differences between male and female ungulates. And again, we can't say anything about that underlying mechanism. Okay, so that's all I have. Sorry, I went a couple minutes over.
Oh, that's totally okay, Beth.